See it later. All right. So now we're trying to try poisoning the data. Remember, there's two basic attacks. Poisoning is where you give it bad data so it learns bad habits, and evasion is where you give it a bad instance to label so it puts the wrong label on it. So we're going to poison the data. So here, you prepare a classification model. I think I don't need to do it live. This downloads a bunch of data, and this is, again, the MNIST data where you're getting digits. And so the model is pretty good. You see the correct is 7, predicted 7, correct is 2, predicted is 2. It gets the first 5 correct using a model we've done before. All right, and so you can see the total truth table here. The zeros, it got them correct 82% of the time, but it misidentified them five times, 82 times, and 5 times wrong. Here's the number of errors it made. So what I'm going to do is poison the training set to try to get it to make specific errors here. So you can summarize, here's the training set and the test set. You see approximately equal numbers of all the digits in the training and test sets. So we're going to poison 10 of the ones. All we're going to do is change the labels. If they were labeled wrong, how much would that matter? So here, you just take 10 of the ones and relabel them as 2s. So now it's going to be confused about what a 2 looks like. And so after you train from the poison data, the answer is it has essentially no effect at all. The poison model gets 2 1s and 11 2s incorrect, and the unpoisoned model did the same thing, I think. The unpoisoned model had, there. It got 2 of the 1s wrong and 12 of the 2s wrong. And after I poisoned it, those numbers changed to 2 and 11. So it's actually made less errors after the first poisoning. So that's not very effective at all. Now, if you poison 30 of the ones, so 15% of them are mislabeled, now you actually make a little bit more errors. Now you get 2 and 13 errors. You made 1 extra error on the 2s. So this changing the labels is pretty ineffective. Of course, if you poison 100, it'll start having an effect. Then half the labels are wrong. But this is the simplest poisoning attack to understand, just having the wrong labels. It's just surprisingly ineffective. Now there are much better poisoning attacks, and that's what you'll see down here. If I go to poisoning by gradients, this is the more effective poisoning attack. And here you do the synthetic one, where you just have a data set with dots. And now you're going to learn to separate these two colors, and you're going to find out is there some way to modify one of these input data or add a new input data based on it that would confuse the model more. So you learn it. Here's the fit. Accuracy on test set is 94%. And now, here's how the gradient descent works. See, now, since you know the model, you can figure out what parts of the space are most effective at biasing the model. You know the weights. So you find out there are hotspots where data here would have a strong effect on changing the model. So you can use this MLSEC library to calculate the most powerful poisoning attack. And the most powerful poisoning attack is to move a dot, and there's going to be, here you are, this star up here. Okay, the single poisoning point is put up here. By putting a dot way up here and labeling it blue, we have carefully hit the hot spot where it has the maximum effect, and as you can see, that changed the classifier quite a bit. Now it's tried to curve way over here and fit that area. So that lowered its accuracy from 94 to 93%, and you can poison 20 points. And now you see all these stars are extra points you've added that are carefully chosen to do the most harm to the model, and that can lower the accuracy to a very small number. So that's more, there's more and more versions of this. This is the kind of thing I was talking about. This is smart poisoning, where you carefully make a modification that will maximally confuse the machine learning model. And it's even easier to see if you work not on abstract points, but you work on images you can see. So you take the MNIST data set again that we've used before, and then you view them. Here they are. So you have 5s and 9s. We've taken some 5s and 9s, and we know the correct label of them. And now we're going to make poisoning images. So you train a classifier, then you perform a poisoning attack, carefully choosing what would maximally harm it. And here is what a poisoned image looks like. You just have a few little dots in it. You take a 5 and you modify by adding a little bit of snow, and then you label it 9. That's one malicious image, which when added to the training set will cause it to make some incorrect predictions. And then you can make 5 poison images. You're going to tell it this is a 9, you're going to tell it that's a 5. Notice the little bit of snow on the edges. These are carefully chosen. For some reason, it chose these pixels are important to the model, even though they would not be important to a human. So you carefully put marks where it's going to hurt the model the most, and this will lower. Notice the accuracy went down from 93% to 57% by adding 5 poisoned images that are carefully chosen. And we saw before, even mislabeling like 10 or 20 of them would do almost nothing. So this is the sensitivity of machine learning models. They are sensitive to errors that would not confuse a human. And you can see that if you look at evasion attacks. And here's the one that's probably easiest to understand. We take those same images again. Okay, and now we're going to make images that the model cannot correctly classify, even though it's very good at classifying these. So we train a classifier, and we use, again, the SecML library to do a calculated evasion attack to make a malicious image that it can't detect. And here's what it looks like. It's just an image with a little bit of snow on the edges. So this would not fool a human. It still looks like a 9. I can still see the 5. I can see the 9. But the model gets all these wrong. And that's why I said the fundamental first step, where you took the 784 pixels and treated them as independent inputs without doing anything like finding the lines or anything, created this weird situation where it learned to prefer certain pixels for some reason, so even a small modification of them will completely fool the model. And this is the fragility of machine learning models. They're not doing what a human would do, so you can make a change that would not confuse a human, and it can have a strong effect on the machine learning system. There's another weakness of it, another security flaw. So the question is, how do you prevent this? And boy, I was real happy with this one. It took me a week to get this working. There was a research paper where they worked this out, and the research paper was real hard to understand, and at the end you couldn't even see the punchline. You couldn't even tell it worked. They just had some weird, complicated statistical thing I couldn't understand. And they said, there, we've proven it worked. And I said, well, this sucks, but I finally figured out how to make it easier to understand. So here's what you do. This is called deep neural rejection. What you want to do, see, you could protect yourself from this attack back here. If you look at that evasion attack again, there's an obvious way to protect yourself from this, which is the original images look like this. These are the original images look like this, 5959. They were drawn with a pen on paper. They don't have funny dots all over the place. They just have lines with a pen. They don't have snow in the image. The evasion attack images are weird looking. They've got these weird ghostly snow in it. It's easy to tell that these are not really representative images. These are funny looking images. You should just remove the funny looking images. That's deep neural rejection. And you can do it with machine learning. You have your whole machine learning model here, sorting them, and then you take the output of some of the layers and feed it into another transformer, which will then measure some statistic of it. And then you just combine those to make a statistic, and then you just take the outliers. These are the ones that look funny. You've trained it to detect some parameters of the image, something like the average brightness of the dots, but it's far more complicated than that, of course. It's going to use learning to choose the most efficient measurement, but it's going to measure some parameter of the images and then remove the outliers, the ones that are not normal looking. That turns out to be quite effective. You get the data, you take the first few images and look at them, then you calculate predictions of the unprotected model, and then you attack the unprotected model with these poisoned evasive images, and it is and if you can see, it's getting them all wrong. Out of 20 evasive images, all of them are successful at fooling the model. So it's really, when it's not protected, you can easily fool it with the same old stuff by adding a little bit of snow to it. But if you turn on the deep neural rejection, and you train your deep neural rejection, and then you regenerate attack images knowing the entire deep neural rejection model. It knows all of it, including the deep neural rejection. It's an open source, open model. You make evasive images again, and now it refuses to categorize many of them. -1 means it noticed this was no good and refused to predict from it. So it's not perfect, but it detected 14 of them. So now only 6 out of 20 evasions are successful. So I was very pleased to finally get this working. Now you can see the defense is having some success. All these defenses, you might notice, are pathetically weak. You notice how we talked about how bad they are for prompt injection. It's the first generation of defenses. These are like the first firewalls that just look for the port number. They're really weak. But they're better than nothing. This is the first step. We're in the infancy of developing machine learning defenses. Anyway, all right. Then you can do a lot with large language models. And I'll just point these out to you where you've got a bunch of different ones here you can play with. You can go here, you can try them on Google Colab. If you go to this page, they have got a whole bunch of open source large learning models that you can run immediately. All you have to do is click this link and it will launch it in Google Colab. It'll take about 5 minutes to start, and it'll open a web interface with a temporary web address that's only good for 72 hours, so you can interact with it. You'll get a web interface just down here ending in gradio.live, which is a temporary web interface, and now you can use it like ChatGPT. Why is the sky blue? It'll just answer questions for you. And that is your model running in your Colab. This is important because, as you probably know, and I certainly know from my consulting, people do not want to use those large language models. Models like Gemini and OpenAI, ChatGPT, all the companies, including those machine learning companies, forbid their staff to use it because if you give it that data, it will learn on the data that comes in from the free users. And as we said before, it does overfitting. So if it learned, if you say, here's my company projections, make a PowerPoint slide for me, I put it up there, it's going to memorize that stuff and repeat it to other users that ask about things because they're pretty stupid and they have overlearning. So any data you send to one of those public large language models should be considered compromised. It might spit that data back out to another user. Now, if you pay for GitHub Copilot, Microsoft promises they will not train on your data. So assuming they live up to that, that's okay. But most companies I deal with don't want to take that chance. They want to run their own model on their own server or in their own Amazon server, for example, where they know that their data is never in any publicly available website. And so this, figuring out how to run it yourself on your own control and use it is quite valuable, and quite a few of these projects show you different ways to do that. So this is one way to do it. You can also run it totally locally. This is extremely simple. This thing called Ollama will let you run Llama locally, and I've got it running on here, and if you have a relatively powerful machine like the Apple M1, this is not the latest one, this is just the M1, it's pretty fast. I've got it here, so if I do Ollama, run, say Llama 3. 3.1 is the very latest one, and I think I've already downloaded it a while ago, so I can run it locally on my Mac M1. And there it is. Okay, it won't let me run that one. I wonder if I can run Llama 3. They've updated something, and it would take a big download. I'm not going to do that. But I'll go. I got Llama 2 and Llama 3 anyway. And that's what it looks like when it's working. Okay, now it's ready. Now I can say, why is the sky blue? And you see it's coming through pretty fast. It's giving me like a couple of words per second. This is all running locally. This is not in the cloud. And so you can now do a lot of things. Now I can interrupt it with Control-C. Now, of course, I might as well mention something else. There's good fun. Here's one of the problems that will show you how stupid large learning models are. If I say a man and a dog are on the bank of a river. The man, let's see, river, you don't actually have to spell too well, but anyway. Okay, the man has a boat. How many trips? Take the man and the dog across the river. Obviously, it's one trip. You put it in, and it will all tell you the wrong thing. All of these are too stupid to answer. See, now it does give me 2 trips. Man takes himself across the river first, then he has to go back to pick up the dog, making a total of 2 trips. So in either scenario, it will take exactly 2 trips. Now, often I'll get 3, sometimes 4, sometimes 5, but never 1. And it's important to understand why. The large learning model does not understand the question. It has no idea what you're talking about. It doesn't know what a man or a dog is. It doesn't know what a boat is. It doesn't know what a river is. All it's doing is taking these words and trying to find some similar words somewhere. And there's a famous puzzle on the internet. 1,000 times, where you have a man and a chicken and a dog, and if you leave the chicken with the dog will eat the chicken, and your boat can only carry 2 beings, so it takes some combination of trips, like 3 trips, to do it. So all it's doing is finding examples that match this text and seeing what text will come after it. It doesn't understand that this question has a simple trivial answer. It doesn't understand anything. It's just returning these words into vectors, putting them in a high-ordered dimensional space, about 700 dimensions, and then it's just fitting a curve through those vectors with a support vector machine or some simple model like that. That's all it's doing. It's just drawing a line through the words like they were numbers and predicting more numbers from it. And you can see how this process works. So anyway, this is how you run it locally, which is a good thing to do. Then you can make a RAG. Now, RAGs are really important. When I first heard about these models, I thought what you had to do was fine-tune them. Now, you can train a large language model on all the data on the internet, which they've done, to make these ones, and then you could fine-tune the training by training it again on your company data. That's one possible technique. There are good reasons not to do this. For one thing, it takes powerful machines. It's a lot of work. For another thing, it has unexpected bad side effects. One of the many bad side effects is if you retrain a model, it will forget the earlier training. So if you train a model like, say, Open ChatGPT, it's trained to write good language, because and it's also trained not to say racist things, not to tell you how to build a bomb, not to code malware. It has security barriers trained into it. But if you were to retrain it to learn your company data, it will forget the security barriers from before. Because when you retrain it, it adjusts all the weights in the neural net, and since you can't understand what the weights do, there's no way to protect the weights and say, don't touch these, those are the security barriers, only train these ones over here to learn the new stuff. Because the model is not interpretable, you can't protect it from forgetting old stuff when it learns new stuff. We're going to come back to this. That's a weakness. Is it working again? Okay. All right. Let's see. There's a theory that this thing is working again. Oh, good. All right. So, so this is one technique which I thought I was going to have to do, and I couldn't find any easy way to do it. And then I learned this has fallen out of favor anyway. For this reason, a lot of people do not want to retrain pre-trained models on your new data. What you do is you make RAGs, like Microsoft Copilot, Retrieval Augmented Generation. Your model is just trained on generic data on the internet, but then you have another thing which Microsoft calls Microsoft Graph, which hunts through your specialized data and finds relevant information, and it adds it to your query. So you send to the large language model, consider this extra information, now answer this question. So it considers both the information proprietary to your company and the generic information it found on the internet and combines them together. And you can make your own. It's really quite effective. So here, you can make a RAG without even a large learning model. Let me run this one. Let's see how it looks. All right. Let's see there. Nice empty one, ready to go. All right. What this does, it just has like 10 recommendations of a fun activity to give. And then it'll take a question, and it will just find the one that matches. So out of the leisure activity you like, say I like to hike. And press enter, and now it says go for a hike in the Mitre scenery. Now all it did was it took the words you put in and it counted how many of those words are in each of these. That's called Jaccard similarity. It found the line of input that matched the data you type in. So it's like an incredibly primitive rudimentary search engine, like grep. Right, but you can add a large learning model to this. That's RAG number 1. Now by the way, let's see a flaw with RAG number 1 before we go off to something else. All right, if you run it again, okay, and now I say I don't like to hike. I can spell it, okay. Then it tells you go for a hike, because it's stupid, right? It doesn't know the word don't. It just found the word hike matched it, it's done, it matched it. So this is the problem. It doesn't understand anything in a simple way. So we would like to make it smarter. So we're going to make it smarter with a retrieval augmented generation. I'm going to do it with my local Ollama. So I should have Ollama running. Let me try my terminal. I'll just give it Ollama serve. This will serve it on a local API. It's already running. Okay, on 11434. Okay, it's already serving, and I think it's probably serving Llama 3, whatever I started it with. So now I can write my next reg, which is going to be here. And actually, I see I should be running this locally, not because I want it to reach my local machine. So I'm just going to go make another terminal and make a directory, defcon, and go in there. All right, now I'm going to nano reg2.py. All right, and so what this is going to do, I'll just run it and then we'll talk about how it works. This is going to Python 3 reg2. Okay, what's the leisure activity you like? Say, I like to hike. Okay, here's what it makes. It makes the prompt adding extra information. You are a bot that makes recommendations. You answer in short sentences. This is the recommended activity, which it got from the Jacquard similarity. And then it says the user input here, and then it says compile a recommendation. And look what it does. It now writes something which is not exactly equal to the input data that's good. And this one is smart enough that it understands if I say I don't like to hike. Okay, remember, the recommended activity is go for a hike, because that's the Jacquard similarity. The stupid grep search found this data, and it added that data to the prompt, but the LLM was smart enough to realize that this word don't matters, and therefore it didn't tell you to go hike. It found something else. So this is what's going on in Microsoft Copilot. This is what retrieval augmented generation is. I don't have to retrain the model. I just add extra data to the query so the model has some context. All right, and it's pretty easy to do. All right, and now you can make reg number 3, which is more realistic stuff. I downloaded a whole bunch of dangers of AI from the official NIST US government statistics, like 80 of them or something. And so now you can ask it questions and it will give you reasonable answers. So you can ask it, what AI risk are you interested in world domination? And it will give you a discussion of whether AIs are going to dominate the world and such. So, you know, you can actually get fairly reasonable stuff here. And like I said, this is very important to me because this is what my clients want. They want something customized to their corporate data and that doesn't expose their corporate data to the internet. And a reg is what they want. That's why Microsoft Copilot is a big hit. All right, so that's this, and there's a couple more to try here. This stuff here is how you can understand how they work. This 127 and 129 are how the large language models work. First, they make tokens out of words. So you have Napoleon revolutionized military organization. This is what it does to tokenize it. It puts a CLS, the mark start of a sentence, a special token for that. Then it takes the words and turns them into tokens. And it can do it by letters, it can do it by words, it can do it by parsings of word. This is one way to do it. Then it's going to embed them in vectors in a higher order space. And this is the part that's always seemed like magic to me. It puts vectors in a higher order space that represent the meaning of the words, in the sense that words with similar meaning are near each other, and words with different meaning are far from each other, and words with similar differences are preserved. So if you take the vector from king and go to man, and you start at queen and move that distance, you'll hit woman, or close to it. So not only are meanings represented, but relative meanings are represented in that vector space. And we're going to see how this happens. So you can tokenize some sentences here, and you'll just see the tokens here. It makes up basically random numbers, but notice the period is a special token, and the end of a sentence is a special token, and it did take revolutionized and make that 2 tokens. The modifier for this word was considered a separate thing. Now you do masking. You just mask 15% of them, replace them with 103. This is how you do it, and now you know the right answer, and you train your model to predict it. So you have you train your model to predict the missing word, so it tries to guess. This is the one artificial intelligence, MASH, takes over the world. It guesses what should be there. Can for 20%, or for 30%, will for 18%, and so on. This is where it learns the content. Then you do the sentence sequencing. You take 2 sentences, and half the time you put a random sentence here, half the time you put the right sentence there, and you train it to correctly detect whether the sentence is right. So that's the game, and now that you've got that, you can do things like do movie review sentiment. This is another, people take a whole movie review, and they want to say, did they like the movie or not, based on like paragraphs of text that ramble. And so the original data came in with these things and a sentiment score, and so you can do sentiment analysis with the BERT is this tokenizer, bidirectional encoding, where it takes the words on the right and the words on the left and uses them to guess the word in the middle. Anyway, you can do sentiment prediction, read whole pages, and this is of course real important for a lot of things, like politicians and people that make products. They say, go scrape like Twitter and see do people like our new product or not. And you've got all this blah blah, boil it down to one number. How many people like our new product and how many people prefer the old one, by scraping all the chat rooms in the world and like trying to do sentiment analysis. This is really important. All right, the other thing that you need to know is how that embedding worked. And again, I was very happy to get this working. It took me, I think, more than a week to write it up. This is the missing piece. This is the essence of that. Attention is all you need. How does it know the meaning of words? And this, I think, is really important because you understand what it knows and what it doesn't know. So here, you take a sentence, and here you load the BERT tokenizer that's pre-trained. There's a BERT model that's already trained, and here's some of its words and its vocabulary. It has a certain number of words it knows. And now you can tokenize a sentence. So here's some. After stealing money from the bank vault, the bank robber was seen fishing on the Mississippi River bank. Now the point here is, this bank refers to a place with money. This refers to a place with money. This refers to a pile of dirt. They're all the same word. So you want to have a model that's smart enough to know that bank here is different than bank here. So you tokenize them, and now bank is 2924 every time, 2924. So now you embed the words with BERT, and then you get the token vectors. You get the 22 vectors referring to each token. And here's what the vectors look like. And you can see this bank is 3 minus 1, and this bank is 3 minus 2 minus 1 because it's the same, but this bank is 1.5 minus 1 minus 0.5. It detected from the context that this word had a different meaning. It's a different vector in the space you're working with here. And so now you can compare these vectors. And one thing to do is the cosine distance is one way to compare two vectors to see how close they are to pointing in the same direction. And so you can calculate this thing called the cosine similarity. 1 is when they're very similar, 0 is when they're not similar. And so you'll see for different meanings of the word bank, you get 69% vector similarity, but for similar meanings, you get 94% similarity. So it can't discriminate them. And now you can do this. You can take this sentence, a boy becomes a man and a girl becomes a woman. And you can predict things. You can eventually make a vector for man and a vector for boy and take the difference, and then make a vector for girl and a vector for woman and take the difference, and show that those two differences are very similar. So it's encoding this, and this is what I didn't understand. I didn't understand how they could ever make this meaningful categorization without having humans sort all the words. This is how they do it. They just do it by comparing it to words around it in context. With this technique where you mask some of it and predict the missing word, it's able to predict patterns, and from that it can find out what words are similar. It's kind of obvious to understand. If you take the example back here of when will machine learning take over the world or something, it's trying to say, then how many words would fit in there? Well, it can take its database and say, well, how often would the word can fit in there? Some other word would fit in there. Well, that means those two words are kind of similar. And you can use that kind of pattern just by taking a pile of unlabeled English data and running it through this model. You can create that vector tokenization, which, by the way, is about 700 dimensions that BERT uses. A 700-dimension floating point tensor is all it takes to encode the meaning of an English word. And that's how large language models work. So that's good stuff. Now, by the way, if you're not automatically generating code, you should be. All the pros are. And so you can use GitHub or you can use Codium if you don't have an EDU account and get it for free. And then these things will go in Visual Studio Code and they will just write the code for you. So let me just show you that if you haven't seen that. Visual Studio Code. I'm going to be teaching a coding class next semester, and the first lesson I'm going to tell them to use these things. I mean, obviously we should be using them. So if I go to, I've got extensions here. Here I've got the Codium AI Assistant. I also have Codium Copilot. And I don't know if it's got to do something that's not going to work on this network, but I should be able to do it. If I go here, I should be able to make a new file. All right. And I should be able to say like prime.py. Okay. All right, and now I can just define a function called isPrime, And I think it's not working in this room because something has to finish installing here, which is rude. But anyway, I'll just show what it should do. It should write the code for me right there. All you have to do is give it any information about what you want, and it will automatically write the code. You can put a comment in describing what you want, or even just a descriptive name. So when I got a good enough internet connection so it runs, then you can go down here. Yeah, looks like definitely the internet connection is the problem. Anyway, well, as soon as you tell it, you're going to write a prime number. It will write all the code for you right away. Let me see, there we are. So all I do is write def is prime, and it then fills in the n, the colon, and all this just appears there. In fact, maybe I have to put in the colon n. It might work here. Let's see. Is prime of n. Nope, it's not working here because I think something to do with the internet. Because this is actually not working on a local LLM. It's sending it off to something in the cloud. But the point is, when you're running on a fast enough network, it will write the code for you, and it's pretty good. So you can just writing a big complicated thing will usually get it wrong, but a simple function like this, it will get it right. And really all it's doing is it's sort of speeding up the normal process where I would Google and find a Stack Exchange article or a manual page to copy. It's just doing that for you automatically. It turns out to be extremely helpful. And so there's a bunch of those, and I have a bunch of challenges I've been using for years to teach Python, and learning how to do them with these code is pretty good. You can also just use large language models like Gemini to do writing your code too. And they all seem to have similar rates of success. But there's a couple exciting ones I wanted to show you here. Just let me step out a few minutes and go to the bathroom. And we got an hour, a little more than an hour left. I'm going to show you two more things, which are quantum computing and large learning models, and Kolmogorov-Arnold networks, however this thing is, which are the new thing to replace deep neural networks. And the advantage of these is they are more interpretable. So they should be free of this part where we can't control them or understand how they work. So I'll demonstrate both of them, but in a few minutes, about 10 minutes. I'll turn this off if I can figure out how. That's off. Good. Good. Thanks for getting this working.
Yeah.
All right. Oh, I should put the scores up. See how people
Put this on the charger while you're
Sure,
in the
people are moving
bathroom.
along. Yeah.
Yeah. Feel better. Enjoy. All good. Thank you though. Get some good rest and hope you can enjoy the rest of it.
I'm leaving early.
Sure.
She got his permission.
Oh yeah. It's totally
I
fine.
want to make sure you guys know.
Thank you.
I was going to try to talk to the Brighthouse people.
Oh yeah. They're really nice. They're really, really nice.
I'm actually going to try to ask him what I could play with, like, part of our kind of meeting is to have like somebody there play vectors and we just as one of our meetups.
They probably will, because they actually back before the pandemic, when we were still teaching on campus, they actually sent me a bunch of decks, and yeah, they're awesome. Hey,
Isn't it?
yes,
So what is the community college's name?
sure.
City College
Oh,
of-
there's City College of San Francisco, and actually those are all Sam's courses are all online there. But then the one statewide one is Calbright. It's CALBRIGHT. And it's we're still pretty new and still in startup mode. So right now it's you can get your A+, Net Plus, Security Plus, and we're about to add Pen Test Plus and Cybersecurity Analyst.
Yeah, that would be something. Cool.
Nice.
So it would just be like a community college, I guess.
It is, but it's different because it's all self-paced. So we're not on semester system. It's rolling admission, and so you can kind of do it at your own pace. Like you can burn through it in a couple of weeks, or you can do it on the slow boat.
Yeah, that would be great.
Yeah, absolutely. That's really cool. Yeah, good luck. They're very approachable and nice.
Yeah. So Objective Society is there between, I think, noon and 1. So I figured if I leave now, I can catch him.
Yeah.
Let's take a look. I think we have time. But I figured, I think we got it covered here. There's like very, very minor troubleshooting.
That's why I said there was no reason. Yeah.
Yeah. All right,
This one was easy.
Yeah, this one was easy.
Some of them have been very.
Like
Some of them
intense.
some of them we've needed everybody, but this one's good.
Yeah. Well, it was great seeing you, and I guess we'll definitely do a meeting or get in
For
touch
sure.
for the
For sure.
Mises chapter thing.
Yeah, and probably may even see you again this weekend.
Yeah, that's right. Sounds good. All right.
Bye. Have fun.
I left this thing recording.
Bye, Sam.
Okay, good.
Oops, sorry.
No, it's working.
I was just charging it
Yeah, that's
while
good. That's
you
a
were
good
in the
thing to do.
bathroom.
Yeah, that's fine. I left this thing recording.